So now we will derive, as we did before, for waves traveling in the same direction, the interference of the two waves traveling in opposite directions that, as we just saw, can create these interesting standing waves. And so we'll take, again, one wave, this blue wave, traveling to the right, and we'll call that y1, and it has, again, a general wave equation of an amplitude a times sine of its wave number k, position x, minus omega t for a wave traveling to the right. And we'll take another wave, a red wave, but this time traveling to the left, which we'll call y2, and it has an equation similar. We'll use the same amplitude a and the same wavelength and frequency, and these waves are traveling just in opposite directions, so the only difference is the plus. And we'll just keep these two waves to have opposite directions and add them together. y1 plus y2 gives us the resulting wave, and so this is the factor out amplitude a, and we have the two equations, sine of kx minus omega t plus sine of kx plus omega t for the wave traveling to the left. Again, we'll use a trigonometric identity to simplify this. And here we can see that, again, we have the sine of something in here called alpha, and we'll call this thing in here beta, since they're different. And the trig identity we'll use is that the sine of one quantity alpha plus the sine of some other quantity beta is equivalent to 2 times the sine of 1/2 quantity alpha plus beta times cosine of 1/2 quantity alpha minus beta. And so if we apply this trig identity to this sum of y1 plus y2, we get the amplitude a times this factor of, well, bracket 2 and sine of 1/2, and then of this alpha term, kx minus omega t, plus the beta term, kx minus plus omega t for beta. And let's just keep the brackets there for sine, and then we'll do the cosine in the next line, multiplied by the cosine of 1/2, and again times alpha minus beta in this case, so kx minus omega t, put these in brackets, minus kx plus omega t. And if we simplify these a little, what we can see is, well, the minus omega t here plus omega t in the sine term cancel, and the kx minus kx term will cancel each other's in the cosine term. And what we can see is the result simplifies a little bit to bring the 2 out, times amplitude, sine of 1/2, and the kx here and kx add, minus omega t, give you negative 2 omega t, so we have times 2 kx, and times the cosine of 1/2 and of minus 2 omega t. So this is the cosine term, and here's the sine term. And we can see the half and the 2's in both of these cases cancel, and what we have is the sum of the two waves is equal to 2 times the amplitude, sine of kx, times cosine of omega t. And just like with the two waves traveling in opposite directions, we have kind of two terms here that we can see. We can see that the 2a sine kx for a given position of the wave simply gives us an amplitude term for a given position, for a given x value position. And then this term just changes with time. So it's a harmonic function oscillating with term. So this is the oscillating term. And the characteristics of this are a little bit different than before, where we saw two waves traveling in the same direction. We can see what the effects of the amplitude term can be. For example, if the term inside the sine function kx is some integer value of pi, again n is an integer, then i.e. 0, 1, 2, 3, etc., then what we get is a term that has 0 amplitude in the amplitude term. And these have a special name for standing waves. These are called nodes, where we have 0 amplitude. And you can also see if that amplitude term in the sine function kx is equal to some half integer multiple of pi, again n equals 1, 2, 3, 0, 1, 2, 3, etc., up to infinity in integers, you can see that you get a value of 1 and therefore the maximum possible amplitude. So this maximum amplitude is referred to as an antinode, so the opposite of a node. And so you can have multiple nodes along different positions x, multiple antinodes. So you can see that the interference of these two waves, resulting interference, could look something to the effect of where you have antinodes in these parts, where it is just oscillating in these sections based on the oscillatory term. And you have in other sections nodes where your amplitude is 0, which is what we observed in the earlier simulation.